All right, in this video, we're going to talk about set operations. So just like in our logic unit, when we talked about propositional operators, in which we started to combine those propositions P and Q, same here, we have sets, all those definitions in the previous section, and then now we can start to operate on them or combine them in some sense using the union operator, the intersection, difference, complement. We'll talk about disjoint sets, and at the end, we'll finish up with Cartesian product. Again, this section is a lot of definitions, so I just wrote them ahead of time. Pause the video if you need to write down the definition as well. So definition 4.31, we have the union of two sets, and you can think of this as the OR. Just like in logic with and an OR, union is kind of like the OR. And is the set containing elements from either A or B. So if we have this Venn diagram here, we have our two sets A or B, then we combine them. And basically, it just takes all of the elements of both sets. And that's denoted with a little u, b, and in set builder notation, it would be x, such that x is in A, or x is in, sorry, that's wrong. X is in A, or x is in B. Nice. And that or is inclusive. Next up, we have the intersection of two sets, A and B, and this can be thought of as the and or the conjunction, just like in logic. So the intersection is where the elements is where they intersect and where they are in both sets. So it's a set containing elements that are in both A and B, and then A has this upside down U, A intersect B, it's X, such that you can either use a colon or the line. I'll try to be consistent here. X such that X is in A and X is in B. And when you have this Venn diagram, it's where they overlap. All right, another definition we have is definition 4.37. That's the difference or the set difference of sets A and B is a set containing elements from A that are not in B. So it's kind of like you have the both sets and then you're subtracting away B, including those that may be in both A and B. So the book uses this notation A and then like a / B. Some books also use A minus B. Doesn't matter. So, but we'll try to be consistent and use the book's notation. And it's X such that X is in A and X is not in B. So that's all these right here. Right, you're in A and you're not in B. And then we also have the complement. So let A be a subset of U, and U is some universal set. It's just a bigger set that A may be part of. The complement of A with respect to U is just the set difference. So it's U minus or U / A. It's denoted with a bar over top. So A bar equals X in U, some universal set such that X is not in A, or X is not an element of A. So we have A and B here is basically everything but A. A simpler diagram would just be where you have A is that circle there, and then everything outside of that set A would be A bar. So either one, but if you have more than two sets, again, it's just everything outside of A. And then we have the definition of disjoint. So two sets are disjoint or mutually exclusive. Those words can be used interchangeably, either disjoint or mutually exclusive, if A intersect B equals the empty set. So remember, this is the empty set. That is, if they have no elements in common. So the picture for disjoint is a little bit different than what we've been having so far. I'll give myself some space and draw it right here. So if we had disjoint sets, we don't have an intersection. So basically they're two separate sets out here, A and B, and notice they have no intersection. All right, just a small quick example. So if you need to pause or go back to those sections in the video, make sure you write all those definitions down. So an example, using those definitions, we have A equals the set 1, 2, B equals the set 3, 4, 5, and C equals set 2, 3. A intersect B would be 2 because they both have 2 in common. No, they don't. I don't know why I wrote that. That's wrong. Let's fix that. So what set has an intersection of 2? I know I had that in mind. Oh, A intersects C. Good. A intersects C equals 2, and B intersects C equals 3, because they both have 3 in common. A intersect B, on the other hand, that's the empty set. Okay. And if I were going to do, let's do a union, since we're here. Let's do B union C. That is the set 2, 3, 4, 5. And notice how I eliminated any repeat elements, which is one of the definitions of sets, right? We just combine them in the union. We combine the elements from both sets in the union. We just dump them in there, but we have to be careful to eliminate or just ignore any repeat elements. So that repeat element would have been 3 in this case. So I'm not going to write it twice. So this is the correct way to write the union. All right, here's an example, a little bit more involved, a little bit more thinking. Let U be the universal set of integers. A, the set of prime integers, and B is the composite integers greater than 1. Okay, and let's do some examples. So first off, let's do the problem A union B. More prime integers are defined in this book to be greater than 1. So let's first write down what sum of A is. So A is 2, 3, 5, 7, 11, and all primes. And then B, on the other hand, is all composites greater than 1. So we have 4, 6, 8, 9, 10 composite. So A union B, well, that's the primes and the composites greater than 1. So we really just have all these numbers. So forth. So basically it's all integers greater than 2, or greater than or equal to 2. So I'll say greater than 1. Because you're either prime or you're composite. So the union is going to be all those integers. And that, I think, would be a good way to describe them. But if you wanted to get technical and practice some of this notation, well, this is z plus, so the integers, positive integers, but minus the set difference, taking away that one element. Okay, so that's what A union B is. Let's do A intersect B equals the empty set. They have nothing in common by definition of prime and composite. Good. Let's look at A bar. So everything not in A, really. So again, I'm going to look at here. A is the set, color in blue here. A is this set. So what is not in A? Remember, the universal set is all integers. So first off, we have all the negative integers. We have 0. We have 1. That's from the universal set. That's not in A. And we can't say 2 is in A complement because 2 is in A after all. But then we start getting all the composites basically. So here is really Z negative. Then we have 0. And then we have the composites. So another way to write this, and these are all disjoint, right? Z minus is disjoint from 0, which is disjoint from all the composites. So we can write this as a union. Okay, so that's a good way of practicing union of these three sets. We have the negative integers, 0, and then B, the composites, and that's what A bar is, or A complement. And I'm not going to go through it in as much detail, but I encourage you to think about it and walk through it yourself. B bar, or B complement, is going to be this set here. And I guess going back to here, I remember the composites are greater than 1, so we don't combine those, so we really have these two singleton sets, so I should have added this here. All right, so those are all the set operations. It's also popular to, or not popular, but a common problem is you're going to have to count the number of elements in some sets, and they may be overlapping and may have an intersection. So let's go through one of those examples together. So here's an example. Let's say you have 50 followers on your social media account. 25 are Gen Z followers, and 30 are dog owners. So maybe you're trying to create a channel or some sort of social media account that has Gen Z and dog owners. So you're attracting these types of followers, and you're getting this data back in your analytics. And then 10 are both Gen Z and dog owners. And your task is to determine A, the number of followers. I won't call it A because that's going to confuse us. So let's call it just question 1. Determine the number of followers that are Gen Z or dog owners. And question 2, determine the number of followers that are not Gen Z nor dog owners. Okay, so first we need to just set up some set notation. So our universal set, that size is 50, right? These are our total followers. And then we have the subsets, or the sets that live within that universal set, are the Gen Zs and dog owners. Let's say A is the Gen Z and B is the dog owners. So then we know that the size of A is 25, right? There's 25 Gen Z followers. The size of B, or the cardinality of B, is 30. We have 30 dog owners. And what is question 1 really asking? And actually, we have one more little piece of information. We know that 10 are both Gen Z and dog owners. So that piece there, we know that A intersect B equals 10. And question 1, what is it really asking us? It's asking us for the OR, which gives a clue that we're looking for the union. So they're really looking for A union B, or the cardinality of it, and what's that size. So let's visualize here. set up our universal set. We know all of it is 50. We know you have an intersection, so I can draw it like that, A, B. We know that intersection is 10. We know that all of Gen Z should be a total of 25, which means that that piece there has to be 15. And what is that piece? That is, you are Gen Z and you're not a dog owner. Likewise, we have this total piece needs to be 30, which means this piece here would have to be 20. And that there is yes, dog owner, not Gen Z. And so we know now we can count the union pretty quickly. We know that A union B is 15 plus 10 plus 20, which is 45. So 45 of your followers are Gen Z or dog owners. And then question 2 is asking for not Gen Z nor dog owners. And so that is the size of A union B complement, right? It's everything but that union. And we know the universal set is 50. We know that everything inside here on both these is 45. And so that leaves the outside, definitely not drawn to scale, is, yeah. We know that the outside, everything not drawn to scale, is 5. Okay, I think my OneNote is starting to glitch out, so I'm going to have to break this video into 2 parts now. So on the second video, I'll talk about Cartesian products. So we'll continue this section, 4.1.2, and we'll just split it into 2 parts. Part B will be Cartesian product. So log into the next video to check it out.